So how's it going, everybody? Today's video is going to be short and quick. I just wanted to put an update out on what's going on so far. So I haven't uploaded a video in about a month now. I've had some stuff going on in real life. I went to visit my parents and yada yada, so I've been working on the CPU a lot less, but now I'm going to try to, speed through it a little bit more through the following weeks. So, so far, a lot of stuff has been done off camera. Ainsley has helped me hook up the master clock, which connects all of the pipeline registers together and syncs them. That's the hardest part, was keeping everything synced, so all the pipeline registers updated at the same time, synchronously with each other. You can't have the execute stage getting clocked, and then 10 ticks later, the decode stage gets clocked. No, they all get clocked at the same time. It's one big shift register that everything moves from one stage to the next. So we did that, and you can see here, all of the colors with glowstone next to it are instructions that have been decoded and built into the CPU already, which is all of them. The ones with the lanterns are actually what have been tested in a pipeline so far. So every instruction with a lantern has been tested in a pipeline, so that just means I have to test jump and link register. I have my 3 operand branches to test, which are branch of equal to and branch of not equal to. For 3 operand, and then the 2 operand is branch of greater than or equal to 0 or less than or equal to 0. I have to test those out in the pipeline, and then we got to get the load store tested in the pipeline. I was working on that yesterday, but I ran into some issues with the barrels. So I was like coding here, for instance, I set my stack pointer is equal to 63, so load immediate R29 gets the value hex 63, for instance, like that. Load immediate R8 gets the value 5. R9 gets a value 3. And if you look in the MIPS register file, you'll see why I'm using register 8 and register 9. They're actually temporary 0 and temporary 1, respectively. So that's why I'm using 8 and 9. They're my temporary registers. Now my return address I'm saying is 0x0002, hex value 2. So load immediate R31, that's a value 2. So what line do I want to come back to? I'm telling it I want to come back to 0, 1, 2. I'm telling it to come back to this line for some reason. So that might just have to be changed. It's just whatever. I'm putting some value in there. So now I'm saying stack pointer is equal to stack pointer minus 4. So stack pointer is register 29, which we set is equal to 63. So what we're doing is we're going to say bytes 0 through 63 in the RAM are going to be our stack, and bytes, or not bytes, sorry, words 0 through 63 will be our stack. And then 64 through 127 will just be general purpose RAM. So what we're going to do is we're going to say take our stack pointer and decrement 4 off of it, so 63 minus 4 is going to become 59. And we're going to say put 59 in register 29. So we're taking our stack pointer, moving it back 4 words, so we can put 4 things onto the stack. So now I need to wait for the R8 write back from this still to finish. And not only that, I need to wait for the stack pointer result to be finished, so that I can then store R8 at the stack pointer. So I have to insert 1, 2, 3 no-ops, and then it's able to do from this instruction. And the reason you can see that is, let's say I need what's in R29 here, and we're using, it's a good example because R29 is used as soon as possible again over here. We can see that we have the instruction fetch / decode stage. So let's say the clock hasn't, we're sitting on line 0, and the clock hasn't happened yet. The moment we're sitting on line 0, that's the instruction fetch. The moment we get a clock, it takes that instruction fetch and it throws it into the instruction decode. Now we're pointing to the next instruction. When this gets clocked, we're in the decode stage and we move to the forward stage. Then when we're in the forward stage, we move to the execute stage. When we're in the execute stage, we move to the memory stage. And when we're in the memory stage, we write it back. And the moment it's written back is the moment that this is an instruction fetched. So since the result of the R29 calculation back here has been put into the register on the right back here, we can immediately use it for that instruction. So we have to wait a minimum of 3 cycles after writing a register to then use that register. Okay, so now you can see why we have 1, 2, 3 no-ops, and then the store word. So that's what I've been working on. I've been working on the pipeline bubbles and stuff that needs to be thought of when you program this, because right now there's no hazard unit or stalling unit on here. It will be added in the future. That's what these buses will be for. And so you can compare the destination to the source and the 2 source addresses. But for right now, it's not on there. So when you're writing the code, the user has to be well aware of that. Makes it a little bit hard, but at the same time, we don't have to build the whole hardware stage that will forward and do everything properly for us right now. That will be there because we have all the forwarding logic, so we want to use it, of course, but we're just getting it to work for now. So this is what I've been working on. So now I guess I'll show you the master clock. So the master clock is this blue bus that you'll see everywhere, this concrete blue. And so the whole CPU is made out of terracotta, except for some control signal lines, which will be this blue. And you can see, comes in here, like that, it's a clock line. Blue is master clock. So for instance, the time it takes to get this blue signal all the way to here is accounted for in every other clock line. So all this delay, 1, 2, 3, 4, 5. That's why there's 1, 2, 3, 4, 5 takes a delay there, so that this is the same speed afterwards, and when this gets clocked, that over there get clocked, same time. So now this blue bus, you can see if we follow it around. Oh, I'm lagging. Alright, so this blue bus is actually, we can generate a clock pulse here, and right there it says master clock. So if we follow it around, we can see that it goes to this. So any of the wood is going to be a pipeline stage. So the way I did this with Ainsley is we connected all the pipeline stage clocks together and synced those, and then connected the master clock to each pipeline stage to then sync everything that way. So literally everywhere there's a pipeline register here, you have to have a clock signal, and the pipeline registers are wood so that you can make them out wherever they are. So here's more pipeline registers. We have one there, there, and here for the memory write back stage. Before, all of that was put here as one register, but that had too much delay in all this busing to get there. I wanted the register as close to the RAM, so the RAM time it took to get to that register was as short as possible, because that's the thing that's slowing my CPU down the furthest right now. The time it takes to decode an address from the ALU, for instance over here, the time it takes to get an address off of this bus to come down here and tell me what address and RAM I'm reading, and then to put that value onto this bus, get that RAM value all the way over to here, and get that RAM value into a register. I wanted that time to be as short as possible, because that's the longest stage in my pipeline so far, and that's about 22 or 23 ticks. So that's the fastest we can clock this thing then, is 22 or 23 ticks, whatever that is right there. Well, at least for when you're doing RAM operations. So that's the idea, and you can basically see everywhere. I keep lagging out pretty hard, but everywhere there's a wood is a pipeline stage, and we can see these stages here. So we have, I don't know what happened to my signs here. Instruction decode. Oh, they're there, but invisible. Lovely. Huh. Okay, yeah. So this is instruction instruction fetch, instruction decode, instruction decode, instruction forward, instruction execute, instruction execute, instruction execute to the memory, memory to then write back. So I was looking at where the forwarding logic would have to come in through here, and if you can't forward, then you have to wait from write back where then it's available. But if you can forward, then the two other stages you can forward from are this stage and this stage there. So that's why we have this forwarding logic on this stage here, where it comes back this way, and we have forwarding logic there for that stage and for this stage as well. And we can make that forward bus go either onto the A or B side. So there's a little mux down here, 2-bit mux, and depending on the value we put on this address line, it will then select which input is allowed to go to the output, 0, 1, or 2. And that's how that works. So that's what I've been working on lately, is just trying to get, keeping track of all the pipeline stages, getting everything clocked properly. The other issues I was running into is barrels were missing some stuff inside of them in some spots. All the RAM and all the registers were missing them. For instance, the MMIO is missing it here, so I have to add that back in there. And of course, for the other MMIO here, well, this is memory mapped output, and then this is memory mapped input. There's 32 input ports and 32 output ports for a total of 64 I/O ports. And right now you can see that we have a multiplier hooked up. It's a 16-bit multiplier that produces a 32-bit result. So two 16-bit numbers are an input, and then two 16-bit numbers are a result. And then the other thing I'm working on hooking up right now is just a vector screen, XY screen. Then we'll have the line drawer hooked up behind that, another module of the screen hooked up onto that. And yeah, that's the goal then, is to start writing some code for this that'll actually work. Then, of course, I need to finish the assembly. I have to restart the assembler for this new instruction set, which is really easy. The assembler I've been working on is universally modifiable, which is really nice. The functions and everything written on it, so you can make anything custom with or whatever you need. So that'll be really easy. And then once I have my own assembly for this, the goal would then to be, you write a program in C++. You convert that C++ code to MIPS 32 using the GCC compiler on godbolt.com or .org or whatever. Then you can take that 32-bit MIPS assembly and hand convert it to the language that is this, which is 16-bit MIPS basically. It has the full 32 register set that MIPS has, so the registers are exactly the same. They're just 16-bit instead of 32-bit. So basically you can do everything that MIPS can do just on 16 bits here. And obviously it's Minecraft, so you're not going to get very high clock speeds. So I calculated that for this to do Mandelbrot, if I had a hardware accelerated unit on the output that would actually do the iterations, it would still take 150 hours to plot a 64 by 64 image of Mandelbrot. And that's just one image, one frame. 150 hours in Minecraft for one frame. So not really quite worth it. And yeah, of course, then the clock also has to make its way into a few other spots. So the clock has to come over to here and update the program counter, which is this. And, you know, so it tells it when to grab the next instruction. And the clock also has to come to the registers to clock the register if data was being told to clock in there. And the same with the RAM. So basically, the clocks are all synced, which is like the first time I've ever built a CPU like this that wasn't janky as hell. Every other CPU I built, the clocks, I just added more delay as I needed to, and I just stuck more delay on wherever I needed it, and then just slowed down the CPU just to make it work. This is like the first thing that's like I built that's timed really well, like really well timed. Like this, I guess I'll show you that there's signs everywhere here unless they got edited or broken. But counting all, yeah, they got. God dang it! I don't know what's happening with metadata on stuff. The signs being corrupted, the barrels losing their signal strength. Oh, that's so frustrating, man. All of these signs had ticks written on them, like how much time it took to get to each stage and stuff like that. Anyway, I think we synced it so each one took a max of 8 ticks of delay, and that's what these signs down here. There's no signs in there anymore. Yeah, so from the master clock going into any pipeline stage, it took 8 ticks. So we had to sync the master clock to 8 ticks to everything, which is pretty doable. Since it's pipeline, that latency doesn't matter. And yeah, so this is just like an update video on what's going on. Oh, and I guess I should mention up there, this is going to be a terminal. Nano and I are working on some sort of way to have like a you can print some stuff to the terminal. You can print like a register to the terminal and tell it that this register is in the format of a character, and it would take that value, look up a ROM address of the character that's stored at that address and display that on the screen. Or it would say, no, this is the data in this register is a value, it's an integer, display this integer instead. So the goal would be to have a console that you could print values from registers to the screen and tell it what kind of format that is, so it knows whether to print a character, for instance, an integer or double float, that kind of crap. Obviously, we're not going to have that, but that's what I mean. I want to be able to have that kind of functionality into this. And then I also want scrolling, so you know, it goes to the new line, so you only see what's currently on here. But if you wanted to scroll back through the history, you would be able to. So Nano and I are working on some sort of way to do that. And when I say Nano and I, it's really been Nano so far, just doing that, because I've been focused on actually getting the CPU working. But yeah, other than that, it works. I ran Fibonacci in this. it wasn't really fun to do because it's really data dependent. So you can't really do a lot of stuff in between the cycles when you're waiting on stuff. You need to wait for the write back to then do something with it. We saw that took 3 no ops, so that's not a lot of fun. What this is really fun is for when you need to do a lot of crap at once, and you need to manage how far behind each instruction is. So if I have to insert 3 no ops, but I can actually do something useful in that space instead, let's insert the useful instructions into that space instead. So that's kind of the programming thought here is to keep the CPU doing stuff and try to minimize the amount of no ops, and reorganize the code in such a way that it would do that. And yeah, this is basically going to support the entire MIPS 32 instruction set, just converted slightly different. For instance, I don't have 16-bit immediates, I have signed 15-bit immediates because I'm using the most significant bit of the immediate as like a select bit to tell me whether I'm using this source or the immediate as a source, for instance. What I could have done is, this was originally 4 bits here, 4 bits for the source, and 4 bits for 4 bits for the destination, and then 4 bits for source 1 and 4 bits for source 2. I changed it to being 5 bits destination, 5 bits source 1, 5 bits source 2, so I doubled my register amounts. That added 3 bits to my 32-bit instruction set, so now I have a 35-bit instruction set. So if I wanted to, I could have made it a 36-bit instruction set and added 1 more bit here for the select, and then made it non-sign extended. But I already made it this far, and I decided to keep it like that. Maybe I'll look back on this and say, you know what, we'll get rid of that sign extension and just do a full 16-bit immediate, because that's actually kind of easy to do right over here. I'll just have to take some thought into how I want to actually execute that, because here's the most significant bit. So it takes the bit below that, which is whether or not it's signed, and it will have to copy it to the most significant bit and that bit. So we're kind of losing some data, but at the same time I don't think it really matters, because this is Minecraft and we're not going to ever really need to have access to a full 16-bit address or a 16-bit immediate. It's ridiculous to think that you need a number that large. So whatever. I'm happy with that. And having the signed immediates allows you to do something like what I showed over here, where you can have stack pointer equals stack pointer plus -4. Right, so we're not doing subtract, R29, R29, and then 4. We're saying add R29, R29, and then -4. We use 2's comp, and we just have to use the add. It just makes things so much easier. Oh, and that's what I was going to before with the stack. So my stack is from address 0 to 63, and the base of the stack is at 63, so you decrement. So this way, if you overflow, basically you go past 0, so you go negative, that's your stack overflow. That's how you can check for stack overflow. Really easy. If you are less than 0. That is so easy to check for. It's a lot easier to do that, in my opinion, than say, we're going to define the stack from 0 to 63 and then check for when it's above 63. That's a little bit more specific to search for. Checking if less than 0 is very easy. So that was my method. That's the reason. My reasoning behind the way I set up the stack. We're at 63 and we decrement our way back, and then if you go past 0, stack overflow. And yeah, that's the idea so far. So if you guys liked and are excited to see what's coming out of this in the future, please leave a like, comment, subscribe, tell me what you want to see this do. The first thing I was going to write after I got it debugged fully was I was going to write a recursive factorial function, just to prove that, well, this thing can do subroutines. Not only can it do subroutines, but it can call a subroutine in a subroutine. Not only that, it can call itself in a subroutine, so for full recursion. And not only that, then I have my hardware multiplier to actually do the crazy factorial calculations that we want. So if I wanted to say 5 factorial, if 5 times 4 is 20, times 3 is 60, times 2 is 120, it would spit it out. If I said 6 factorial, it's going to have to take 120 times 6 now. So this number is going to grow really big, so having a 16-bit multiplier with a 32-bit result actually allows us to view a very large factorial result, which is pretty cool. And of course, the result is a high word and a low word out of a multiplier. So you multiply 2 16-bit numbers together, you get a low 16-bit result and a high 16-bit result. And then to view that, you have to view that all as one number. So I'm not sure how that will be sent to the display, if we're going to make it so that you can display a 32-bit number on the display, or make it only 16. I'm not sure what I want to do for that yet, or make it software where you have to run software, you have to write a subroutine that will convert your 2 16-bit numbers to one displayable 32-bit number. Either way, something will be done. That's the goal. Oh, and the other thing I wanted to mention is I'm pretty sure this is the most powerful Minecraft computer ever, just because of the fact that A, it's 16 bits, and B, the ALU can do anything, including barrel shift, left to right. So if I say, let's say I have a 16-bit number, and let's say I'm using my multiplier, and I have assigned fixed point notation of 1 plus 3.12 for my signed fixed point, like that. So that's saying I have a sign bit, 3 integer bits, and then 12 radix bits. Well, what happens when you multiply we'll use a 4.12 notation just for easier sense. What happens when you multiply two 4.12 notation numbers? You got 8.24 as a result. You double the front and you double the rear. You still 32 bits, so you took your 16-bit number, you multiplied it with another 16-bit number, and you produce a 32-bit result. But you want to get it back down to being 4.12. So we would have to take... so really it's split up between 16 and 16 like that, but we have 8 and 32. So we're going to have 8 and 8 in one byte, and then we're going to have we're going to have so we need to make our 8.24 number as like two 16-bit numbers instead. So that means we have to left shift that top one down, the least significant bit. No, sorry, the most significant word we have to right shift it 8 times, and the least significant word we have to right shift 12 times to get back to our 4.12 notation. Then we have to OR those two values together. So being able to shift multiple times in one cycle using a barrel shifter is super powerful when you have to start managing those bits. You have to start bit masking and ORing them together to generate the value that you wanted as a result. So being able to do, I want to shift this value 16 times right now, or 15 times up right, or 3 times left, or whatever. Being able to do that in one cycle is very, very, very powerful. So yeah, I just wanted to point that out as well. And yeah, of course, the other reason I think it's so powerful is there's 32 16-bit registers. What other CPU in Minecraft has 32 registers to use? And then what other CPU in Minecraft has 128 words of RAM and then 64 I/O ports, which you can use as memory as well. You can write, the I/O ports have registers on them. So if you want to write to that I/O port and use the register on that, you can write to it and send whatever data off. And if you wanted to hook up more storage to this, you can use an address port, an input-output port. So you can say on the output we're going to output an address, and on the input it will return back a value held in a memory bank at that address. So you can hook up a hard drive to this if you wanted to, and then have like data sent to it through another bus. So it's really endless in what you wanted to do here with how this is set up, because it's set up for proper CPU with proper MMIO. So if you were trying to write to a port, it's like writing to RAM. If you're trying to read from a port, it's like reading from RAM. That's why it's literally right next to the RAM here. Alright, I think this has been long enough rambling. Thanks for watching. Hope you guys like and enjoy. Any questions, comments, leave them below, and I'll see you guys next time.